They want me on all the time if ever I buy now. No, that is my chair in my bag. It's actually coming round.
You are very welcome to use these tables as well if you don't want to sort of crick your neck. So absolutely fine. You are very welcome to use these tables here as well. You don't have to do speed dating anymore. Have we got everybody back? Don't think so. 13. That's bad luck.
Can I put myself first here? Half a country than you. Oh wait, Callum. Oh yeah.
Probably gone for a cigarette. No worries. No stress. 15, how many should we have? 17, okay. Oh. Aha! Perfect. We got everybody then. Wonderful, thank you. Hey. Okay, shall we make a start? Yeah, lunch is waiting, right? A most wonderful good morning, everybody. And welcome to my part of this intensive summer school, whatever it's called. My name is Peter Klapper. People usually just call me Peter. If you feel uncomfortable with that, you can call me Dr. Klapper or Dr. Peter or whatever. But usually I don't react to Oi Klapper. Some of my students do that. If you've got any questions, here's my email. So please feel free to contact me if something is not clear or something like that. Just a little bit about myself. As you can hear, I'm not a native speaker. Where do I come from, actually? What do you think?
Sweden.
Sweden? Germany? Yep, I am indeed from Germany. This year it is 30 years that I had this grand idea. I want to see the big wide world, so I came to Kent. And the plan was to stay here for 2 years and then bugger off back to Germany. I'm still here. 2 kids, a wife, 2 dogs, 3 cats later, this, obviously they must do something right. So it's not such a bad place. I'm not, and I want to underline that, I'm not a biostatistician or something like that, but I had the sort of the misfortune of being in the wrong place at the wrong time when somebody said we need somebody to teach statistics to our bioscience students, and I wasn't quick enough to disappear. So it was, yep, Klapper, you're in frame. So anyway, we are going to spend a little bit of time on statistics. Everybody loves statistics, right? Okay. People get very interested in their shoelaces now, right? Okay, show of hands. Who loves statistics? Hands up. Not all at the same time, please, right? Who is a bit scared of statistics? I am. Yeah, okay, fair enough. That's great. So the way who would say that they have already a sort of a decent understanding of statistics? 1, 2.5, something like that. Okay, good. So for the rest of us, it's sort of, hey, we probably heard of a few things, but maybe it would be good to build up on things and, make sure that we are totally on the same page. Are you happy with that? Now, what I want you to do is, I want this to be as interactive as possible. Oh, by the way, this is recorded, so, but it's only for you guys. It will not be broadcast to the wide world. If you say something confidential, please think first before you say something that gets you into hot water with your company. What I want these sessions to be is as interactive as possible. I will ask you a lot of questions, and please do ask me questions as well. And we just take it from there. If it is too easy, right? Please tell me. If it is too, tell me, because we can change things. Yeah, happy with that? Brilliant. I have set up a website for you guys as a sort of a companion website, and I strongly suggest you scan this thing. I hope the website works, because there are lots of topics that we are going to discuss. And does it work?
Yeah.
Brilliant. Bookmark it. There are also calculators on there that you might find useful at the end, because at the end of the day, we have to do a little bit of calculations. Yeah. So please, please, please make use of this resource. I can send you the link, Kirsty, and you can put it up on Moodle if you want. And it basically shows you what we are going to do. So I think I have even, you've seen that from Kirsty. That's the sort of what the plan is time-wise. And what I want to do with you today is really a sort of a basic introduction. We are going to talk about data formats. We'll talk a little bit about this descriptive statistics, what data might look like when they are a little bit more complex, and how we can visualize data, because that's one of the key aspects. You get a bunch of data and you think, bloody hell, so what? Who cares? We talk a little bit about linear regression and logistic regression. You are familiar with logistic regression? No? Brilliant. Good. Then I can tell you something. We will talk about how we can find outliers in data, and also important, what to do with outliers. Sometimes in clinical trials, somebody might have a slip of the pen recorded the weight of a patient as 858 kilograms. And you think, ooh, that's a bit on the heavy side, might go on a diet. And then I was told that it might be quite useful for you guys to have a brief introduction to R. Anyone knows what R is? It's a statistical program language, indeed. Most of you guys will, when you do data analysis, you probably, I was told, the regulator asks for everything to be done in SAS. Is that right? Yeah. That's another sort of statistical program that basically spits out some numbers. It basically tells you, there's no difference between placebo or drug or something like that. The statisticians and the people who are actually doing the analysis, they are not terribly fond of SAS because it's rather clunky, I've heard. And it's a little bit like pulling teeth. Instead, what appears to become more sort of widespread is this other statistical language, just R, just an R. Has anyone had any exposure to R? No? Hey, cool. I turn you into programmers. Brilliant. Okay, so let's work on that. It is, when I started learning it, I thought, oh, bloody hell, this looks so complicated. It's not. It's absolutely simple. And you don't have to pay for anything for that. Right? It's all open source. And it's great. And it can even run on the lousiest of laptops. So don't stress about it. Okay, so that's what we are going to do today. And right, just out of interest, I have a mini data set for you. We do a little drug trial, and we recruit a total of 10 people, 10 volunteers, and 5 of them get a placebo, and the other 5 get the real stuff. So it would be a, what is it called? Randomized drug trial, yeah. Very small, but you have to start somewhere. Whatever these numbers are, I don't know, it could be a biomarker or whatever. And when you look at it, just without any sort of weird and wonderful calculations, what would you say? What is your gut feeling? Does the drug work or not? What's your gut feeling? Yeah, it works?
It's trying to increase the number. Then,
yeah. With the drug, it increases the numbers. Yeah, it looks like it, doesn't it? I mean, it's not that we are looking at the same patient. It's not that before the drug, this person got 1, and after the drug, the same person got 3. It is just, The first 5 people here, you get the placebo. Next 5 people here, you get the drug. And that is our measurements. And you would say there's a difference. Yeah? Who agrees? Yeah? Is there a difference? Okay. Are you willing to bet the life of your unborn child on the statement that there's a difference?
Yeah.
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 Good.
There is a difference.
There is a difference. Okay. So, by the end of this, when I finished with you guys, not today, but on Thursday? Yeah, on Thursday when I'm finished with you, we will reevaluate what happens to your child.
What's his name?
Okay? Or do you have already a child?
I do not have a child.
I mean, this is a personal question, and you don't have to answer that. But you know, it's okay. We will come back to that, and we will say yes, you were right, or you know, I don't know what we do with an unborn child, but you know, okay. So now, of course, I set you up a little bit. Because that's the first thing that we are going to do, that we have a conversation about. And this conversation is, I need to just quickly change the thing that I'm, yeah, I need another document. Okay, the first thing that we need to talk about, and that is where usually, right at the beginning, when you do analysis, when things start to go wrong. I haven't even written anything, but when you do some data analysis, the first thing is that you need to be clear about what type of data do I have. And that is an absolutely essential part, because get this wrong, and your entire analysis is totally pointless. What do I mean with data? Well, we have different data types, and you probably have done that in GCSE or A-levels or something like that, where you looked at data types. Yeah. So the most basic data type would be what is called categorical. Where you just simply assign labels to the data. And the most basic categorical data format is nominal data. Nominal data is just a label without any sort of attached value to it. Just to give you an example, nominal data would be male, female, others. And there is no sort of, how shall I say, differentiation between these categories. That's why it's categorical data. Male is not, you know, more worth than female. It's just different. So nominal data are really the most basic level of data that you actually can have. It's just a label. I've shown you already nominal data. Remember, minus drug, plus drug. That's a label. Yeah. So this would be nominal. It has two levels. Okay, so that's nominal data, no value attached. But of course, we can count, for example, how many patients were in the minus drug or plus drug section. It doesn't mean that nominal data cannot be translated into numbers. But per se, nominal data don't have a value, it's just a label. Bang, stamp. Okay. Another type of categorical data would be ordinal data. Ordinal data means we can actually place the categories into a logical order. So, for example, we can look at, let's say, how many, we can look at Olympic Games, for example, and say at Olympic Games you can win gold, silver, or bronze medal. And you probably agree with me that a bronze medal is not that much worth as a silver medal. A silver medal, you know, is beaten by gold medal. So you have a logical order in it. You have order in it. You can order the data. And that's quite important. With nominal data, we said you don't have that. With ordinal data, you have that. But quite importantly, the order for ordinal data is not terribly well defined. How much more is a gold medal worth than a silver medal? What do you think? It is more worth, we said, but how much? Twice? 3 times? 10 times? Well, we don't know. So there is no clear, we know it's more, but by how much we don't know. That is our ordinal data. You very often find that every day you see ordinal data when you, for example, look at ratings on Amazon. How many stars? From 1 to 5. And this is a typical ordinal scale. Or you ask patients, how bad is your pain level? From 1 to 10. Ordinal. But you can't say really 1 is half as much pain as 2 or something like that. You don't have this comparison. Okay, so nominal, ordinal. Oh, by the way, ordinal data are a real pain to work with in statistics, but they happen quite a lot, unfortunately. Now, of course, we can have what is called scale data, and some people call it numerical data. I mean, the categorical data are also numerical if you just simply add counts or something like that. What do I mean with scale and numerical data? These are usually the data that we are used to, that we are quite happy to measure, weight, height, something like that, right? Where you have a true numerical output. And what we usually find with these numerical data is, again, we can split them into 2 groups. They are sort of mutually exclusive, these groups. The first group is called continuous data. In continuous data, you can make an infinite number of measurements. What do I mean by that? Well, you can measure the height of a person. Let's say you are quite tall, aren't you?
No, I don't think that. I don't think I'm quite.
How tall are you?
Like 5'8".
Okay, how much is that in metric? 176?
Maybe.
107. Okay, let's do 175. So let's do 175. Now, I could also, in the morning, you might be a little bit taller. In the evening, after statistics, you go a little bit like that. Yeah. You could have 176. Can I have anything between 175 and 176? Can I have a measurement in between there? Yeah? I could have 175.2. I could have 175.213, depending on my measurements. And I could have 175.213, 879, 87346, and so on and so forth, right? I've got an infinite number of numbers between the measurements. And that is what is meant by continuous. On the other hand, we can have the exact opposite. Does anyone know what they are called?
Not sure.
Not sure? Obviously not continuous. These are discrete numbers. Yeah? It's not that they have a secret. That would be discrete. Discrete numbers can only have usually whole numbers, but they can't have anything in between. So, for example, if I count the number of people in the room, should be around 20. I can have, if somebody comes in, 21, but I can't have 20.34 unless somebody is pregnant. But we just discount this option. Yeah. So discrete numbers, there is nothing in between. There's nothing possible in between these numbers, between our measurements. Rolling a dice, for example, you either get 1, 2, 3, 4, 5, 6. They would be ordinal, actually, if you think about it. And you can't have anything in between. You can't roll a 2.7. Not possible. So why do I harp on about it? Because when you do data analysis, when you look at statistics, continuous and discrete data need totally different treatment. You can't do discrete data, you can't analyze them with continuous methods and the other way around. Well, you can, but it will be wrong. So there's no point in doing it, right? So always make sure that you actually know exactly what data system, what data format you are working with. Because when people do analysis, this is where things go wrong. The rest might be okay, but if you got mixed up between discrete and continuous data, your assessment will be wrong. There. Okay, so we've got data formats. And now let's talk a little bit about what we do with data. So let's explore the data a little bit. And that is called exploratory data analysis, or short EDA. Some people call it descriptive statistics, but descriptive statistics is not, well, EDA is more than descriptive statistics. EDA is actually also visualizing the data. What do the data look like? And I'll tell you what, why don't we just simply stick to our placebo data? So minus drug. 1, 2, 3, 4, 5, whatever these numbers are. By the way, our drug data, continuous or discrete? Discrete? Sorry? We have no way of knowing.
Just because they haven't got 2.5 doesn't mean they couldn't have 2.5.
What's your name?
Callum.
Callum. Is Callum right? You said discrete? What's your name?
I didn't say it.
Oh, who said discrete? You did? Okay. What's your name?
Hope.
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 Hope. Okay. Group, is Hope right? Discrete, is Callum right? We don't know. Callum. You're absolutely right, Callum. Sorry, Hope. In this case, we have absolutely no way of knowing, because if I said, for example, 1.0, would you still say it's discrete with a decimal point? Well, actually, a decimal point indicates usually that we might have done a measurement that allows us to measure, say, 1.1 or 1.2. In this case, this would be continuous, but if there is just one, we have no way of knowing whether these data are continuous or discrete. It depends on the context. If I say, for example, and this is the number of spots that a person has on their nose, then it would be discrete. If I say this is a biomarker, that just by chance got whole numbers out, but in theory could come up with something else, 1.5 or so, then it would be continuous. So at that point, we don't know. And it has to be taken from the context. Okay, so now we've got this data. We've got this data set. Let's make that proper. And what we can do now, of course, is we can say, well, instead of presenting these numbers when we write a report, what we can do is we can summarize the data to a certain degree. Yeah? With 5 data points, it's not, it's not arduous to present these data. But imagine you have 30,000 data points, then you want to have them summarized. And one of the easiest ways of summarizing data is with what is called the measure of central tendency. And you all have done that before, measure of central tendencies. There are basically 3 measures of central tendency. One is that we just simply calculate the average. Statistics, it's usually called the mean. My maths teacher said that I am only average. I thought that was mean. That was a bad dad joke. Sorry about that. And how do we calculate the mean? We add them all up and divide simply by the number of observations. So mathematically, we would write this as we take the sum. We start with 1, and we end up with the number of observations, xi, use the subscript, means just an observation. And we divide that by n. It's trivial. You have done that before, yeah? Simple. So what we do is we just simply say 1 plus 2 plus 3 plus 4 plus 5 divided by 5. And if my calculator with the fingers has worked, it gives us 3. You are absolutely right, 3. Wonderful. That would be the mean. And that is actually the mean of our observations. We're not dealing with any weird stuff. That is the mean. Now, that's great. The mean, however, has a bit of a problem. Does anyone know what the problem with the mean is? Can you guess what the problem with the mean might be? If we've got some weird stuff in it, then the mean might be a little bit problematic, right? So let's say we have a system where we have 1, 2, 3, 4, 100. Yeah. Obviously, you would eyeball the data and say, oh, this 100, that looks a bit weird. Should that be really there? But, well, you know, this is what we measure for one reason or another. Okay, what would be the mean of that? 22. So the mean equals 20? 22. Absolutely right. Okay, mean is 22. Just add them up, divide by 5. But what you see is that this mean is nowhere near our first 4 numbers and nowhere near the last number. It's somewhere, you know, sort of in no man's land. So the mean is always very sensitive to outliers. And therefore, we need to ask ourselves, should we really report the mean in this case? Because it might give the wrong impression. What would be an alternative to the mean?
Median.
Loud?
Median.
Median. You're absolutely right. We can do the median. Median depends on the number of observations that we have. If we have an odd number of observations, we just take the middle number when we order the data. So if we've got, for example, 1, 2, 3, 4, 5, they are already ordered quite nicely. And we just simply take the middle number of that. So I usually do it like that, 1, 5, 2, 4. Aha, we've got a 3. That's our median. Yeah. Median is very often abbreviated with a capital X and a squiggly line over it. So just in case you see that. Our mean for the data, in this case, is usually abbreviated with the Greek letter mu. Sorry?
That's what mean is.
That is what the mean is. So mean and the median. Now, what happens if we've got an even number of observations? So we might have 1, 2, 3, 4, 5, 6. It's an even number. What we do is we basically take the middle of it. So we have 1, 6, 2, 5. We've got 3 and 4 as the middle. And from that, we take the mean, half of it. So here, it would be 3.5 as the median. Although this number doesn't turn up, but it is halfway between 3 and 4. Yeah, makes sense? Easy. Is the median sensitive to outliers? Let's have a look. 1, 2, 3, 4, 100. Is it sensitive? What do you get for the median for this data set? 3. Hey, look at that. How cool is that? We have something that's way off the rails, but doesn't matter because we can report the median as the same as the mean. Doesn't always have to be the same, but the median is far less sensitive to outliers than the mean. Yeah, so very often, especially when we have data where we have outliers, we do report both. We report the mean and we report the median. And you can immediately see, if I say to you, for example, the mean was 22 and the median is 3, a light bulb should go on and say, oh, they are very different. That means there must be something weird in the data. Yeah, makes sense? Happy with that? There's one more, central tendency, which you very often come across in clinical data. And that is just simply, how often do numbers turn up? This is called the mode. And the mode is basically the number that shows up most often. So let's say we have 1, 2, 3, 4, 5, 2. In this case, the mode would be 2. Because 2 is the number that turns up most often in the data. Yeah? Actually, modes can be quite tricky when you have continuous data, because you might have, 2.2, 2.1, and so on, and that gets a little bit iffy. So be careful with modes. But if you've got, for example, count data, like how many people we have, then a mode is a good descriptor for the data. is it possible for a data set to have no mean? What do you think? Can some data have no mean? No. If we have data recorded, we can always calculate a mean. Is it possible for a data set to have no median? No. Has a median. Is it possible for a data set to have no mode? Yes. Yes, absolutely. If all the numbers are unique, then we have no mode for that. And if you base some statistics on modes, then you're basically screwed because you can't do it because there's, not every data set has a mode. That's why mode is usually not used very often in sort of hardcore statistics. Okay, so we've got a measure of central tendency that gives us a sort of one measurement that sort of summarizes the data quite nicely. We have the mean, we've got the median, and that gives us information about our data set. But I'm pretty sure you agree with me that this is only part of the story, right? This is only one part because it does not tell us how far spread out the data are. It could be, here are two data sets, 1, 2, 3, 4, 5, and we said the mean for that is 3. And here's another data set. Quite boring. What's the mean? 3. And if I just report to you, the mean was 3, you would not know which data set we are looking at. So, and there is very clearly a difference between the data, isn't there? Yeah. So we need another way of describing in addition to the measure of central tendency. And this is called the measure of, and there are different names for that, measure of dispersion or variation. Or you sometimes see also variability. And this basically tells us how much the data are spread out. Yeah? The easiest one that you probably have encountered is the range of the data. And the range is defined as the maximum number minus the smallest number. So in our case here, the range would be 5 minus 1 equals 4. That's the range that we have. Yeah? I can say the data have a range of 4 with the smallest number 1 and the highest number 5. This is how you would report that. And it's quite straightforward and easy. We can also say, we've got our data. 1, 2, 3, 4, 5. The mean equals 3. You can also say How far away, on average, is every observation from the mean? So, how far away, on average, is every observation away from the mean? Okay. How would we do that? So we would take our first observation, that was 1, minus 3. Let me actually sort of draw this to visualize that better. We have 1, 2, 3, 4, 5. And I draw a line through the mean, like that. And what I do now is I basically measure how far is 1 away, how far is 2 away, how far is 3 away from 3? Oh, that's easy. 4, 5. Yeah, basically calculate the average of the distances from the mean. Happy with that? Okay, what do you get for the average? On average, how far are the data points away? Shall we do it quickly? Yeah. So we have 1 minus 3, that's our first observation, plus 2 minus 3, plus 3 minus 3, plus 4 minus 3, plus 5 minus 3. And we divide that by how many observations? We've got 5, right? What do we get as the average?
1.5.
Sorry?
1.5.
No? So you've got -2 plus -1, 0, 1, 2. Oh, we get for our mean, we get 0, right? Wait a moment. Wait, that's weird. That's totally weird, because what this tells us is, on average, our data points are 0 away from the mean. Is that right? Can this be? No, it doesn't make sense, right? Because we see that they are away. Yeah. What's going on? Why do we get 0? How do we get? Very clearly there is a difference, there is a variability, but with this calculation, it tells us no, they are on average exactly the same as the mean. What is the problem? What was the problem that you had in your calculation?
We didn't use negative numbers.
Negative numbers. The negative numbers. That was the problem, right? Because the negative numbers that we have here at the beginning exactly cancel out the positive numbers here. That's why it gets 0. So if we avoid using negative numbers, we could overcome this problem. How do you convert a negative number into a positive number? It doesn't work with your bank account, by the way. Yeah. How do you convert a negative number into a positive number?
Modulus?
Sorry?
Are you using modulus?
Oh, that's yes, you could, but that's very complicated. Something else mathematically?
Times it by -1.
You could times it by -1. Yes. You could also just simply take the absolute value. Yeah. The absolute value just simply says, I don't give a damn about the sign. For me, everything is positive. Yeah. God knows what drugs I had, but yeah, everything is positive. Or there's another way of converting negative numbers into a positive number. What could you do?
You square every number.
Ah! Fantastic idea, Callum. Thank you. We could square every number because a negative number squared gives a positive number. A positive number squared is also a positive number. Hey, cool. Let's do that, right? So, conceptually, what we do is we don't measure the distance here. We actually build a little square. Right? That's a little square. That's a little square. The 3 doesn't get a square because we can't do a square of 0 there. Yeah, like that. And now we ask not what is the difference between it, what is the average? What is the average of the squares? How do we do that? Well, again, like we did above, 1 minus 3, but now we square it. Plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared, and we divide by 5. Yeah, happy with that? Okay, what have we got? 1 minus 3 is -2 squared plus -1 squared plus 0 squared plus 1 squared plus 2 squared divided by 5. And that gives us -2 squared is 4 plus 1 plus 0 plus 1 plus 4 divided by 5 gives us, yeah?
2.
Exactly. This gives us 2. So on average, each square is 2. And what we just did is we calculated a very important statistical characteristic of our little data set. Does anyone know what this is called?
I think that,
Sorry?
I'll guess, is it that standard deviation?
Is it the standard deviation? Excellent answer. Great answer. No, it's not. This is called the variance of the data. Yeah? Come back to that. Hold that thought, okay? This is called the variance of the data. And for our data set, it is usually abbreviated with another Greek letter. It's abbreviated with the letter sigma. It's sort of this squiggle. It's an at sign that's sort of with a little bit of attitude. So our variance, the square, the average size of the squares is 2. And that, for somebody who knows what a variance is, they say, oh, cool, there is a variance there. Can a variance be 0?
Yes.
Are you sure? Can a variance be 0?
No.
Oh, I love it. I love it. I love it. I just, make people doubt themselves. Sorry?
I think it can if all the numbers
Look at that example that I just pulled down. You're absolutely right. If all the numbers are the same, then there is no variability in it. Yeah? We said the mean is 3, and the difference of the square is always 0, so the variance can be 0. Yes? 0 variance means there is no variability in it. So the variance is a very, very useful tool. But it has one slight disadvantage. As useful, actually it has 2 disadvantages. The first one, people usually don't think about. Let's say our data set, these 1, 2, 3, 4, 5, are, I don't know, centimeters. Yeah? So we have 1, 2, 3, 4, 5, and the unit is centimeters, whatever this is, right? Our mean would be 3, and the unit is centimeters. Absolutely right. Our variance would be what we just calculated, 2. What's the unit?
centimeters.
Is it centimeters? Is it centimeters? What do you think? Is it centimeters? Ah, it is centimeters squared, isn't it? Because we squared all numbers. Yeah? Makes sense? It is centimeters squared, the unit. And that's a little bit iffy. Centimeters squared. Everything else is in centimeters, and now this is in centimeters squared. Bleh. Actually, I made a mistake. I made a deliberate mistake, but we come back to that in a minute. Let's get this sigma out of the way first. So, what do we need to do if we want to have the same unit as, for example, our data? Everything is squared, but we want to have it the same thing. We take the square root of the variance.
In that scenario, do you just put root 2?
And in our case, it would be square root of 2. Absolutely right.
You just leave it at that.
You just leave it like that. Or if you want, you can do it as 1.41 or something like that, if you want to, right? So the square root of the variance has a name. It has a name.
Is it standard deviation?
This is called the standard deviation. The square root of the deviation. Right? Now, I made a deliberate mistake earlier because actually, yeah.
Were you going to say that sigma squared is variance?
Yes.
Yeah, I thought so. Yeah.
Yes, absolutely right. Because actually, because the standard deviation is such a common thing, because it brings back the units that we, had tampered with earlier. People have said, well, we want the standard deviation to be sigma. And therefore, the variance actually is called sigma squared. Yeah. So here, our number 2 would be actually sigma squared. And here, the square root of the variance would be just simply sigma. Standard deviation is defined as the square root of the variance. Or I can also write, of course, standard deviation is the square root of sigma squared. Yeah, happy with that? So standard deviation will very often be reported, in this case, 1.4 or square root 2, whatever you prefer. Usually people don't like to type square roots or something like that. Where's that on your keyboard?
You have to go to like subscript, or you have to hold the 2.
You can't really type that on a keyboard unless you use the equation editor, which is a total and utter pain in the, wherever. Yeah. So that is the standard deviation of our data. Shall we do a little break? 5 minutes? Or do you want to carry on?
I want a break so I can stretch out my back.
Yeah, absolutely. 5-6 minutes break.
Should we get a yoga session?
Yeah, we could do that. Yeah, yoga. I'm very sorry for you guys. It's probably incredibly basic.
Starting place. So I can tell you how to calculate standard deviation. So it's a good.
Is it boring? Yeah, just plug it into Excel.
I couldn't do it, but I understand what you're saying.
You can't do it. Yeah. 5-6 minutes. Yeah. I know it's terribly simple, but does it make sense?
Yes, it does.
Yeah, and you have done. I mean, you've done that. No.
No. Statistics. This is like university.
Really?
Yes.
So this is new stuff for you. sort of.
Yes, very much so. So, but it's done in a way to I understand it. Yeah, because it's starting from 0 to where we are now. So yeah.
Wow, how? I'm pleased. Thank you. That makes. Just checking with you guys. This is. Is it too simple for you guys?
I think it's a good
I haven't done-
introduction. Yes,
You haven't done
I
statistics.
haven't done stats since like maths
Yeah.
GCSE, so it's a good
It's
thing.
good, yeah.
It's
Yeah.
good, yeah, thank you.
Okay, so
I think we're like building the
Yeah,
foundation.
Mhm.
Also, I feel like in school we learned standard deviation, but they never really explained what it was.
Yeah.
So now I actually know.
Yeah.
So it makes a lot more sense than what we got taught in A level.
But then look, when I see the other guys, so good. I just like one of the things. So the first night is basically
That's why I only did it.
oh my team.
Yeah, that's I feel like whenever I would be like, that was his first date. Like, that's really really bad. I think I just love people who's like like more rather than like I something that you enjoy, yeah, that's why I just like really. I feel like you either like have a natural flags or like something like that, or like it's true torture to try and like reverse it.
Yeah.
You don't do any good. I feel like it's so bad. I feel like I know people who are like, I'm on day like 100 of doing where they don't know anything yet. It's so much easier to apply it somewhere, which is obviously very nice. People always say that like if you like go out there, yeah. No, I not the right yeah. When you study like a book that apparently is written for like 11 it's not really yeah. Yeah, and then I never go to it. It's like, oh, I don't know it would come back to you maybe if you like somebody spoke to you. Yeah. Okay, I'm picking it up. I went after A-levels, I went to Barcelona with my friends, and we were on the beach playing cards, and like this group came up to us and like, oh, she's gonna play a game with speaking French. Well, I didn't realize it was speaking French, sorry. But I was like, oh, I'm just going to speak English. And speaking to us in English. I was like, oh, I'm going to speak French back. But you don't know what it is. And I recited like my IRP. Just blurted on about whatever stuff I could remember. Like 2 a.m. And they're like, oh, I thought we were trying to do shows. So yeah, it's like continue speaking in French now. But no, I used to swim quite a bit, but I kind of stopped like the love for that for a long time. But I like doing all like books, like that sort of vibe, depending on what we do. But yeah, I do. Is it not for me? Like if you walk around on like a real game, keep up to. Oh yeah, but yeah. So nice, yeah. I remember that. When was it? It must have been like the induction day. Like a couple of years ago. Like so fast. You never like mentioned it before. Yeah. I mean, something that you can't see in conversation. I think it was like Monday to Wednesday. It was just like just went to we left really early on Wednesday because yeah, that's a kind of session. I think it's like a little number, but yeah, see what's going on. My trainer knew at 5 p.m. and shit like 1. Yeah, what happened? remove it or you can change it. And I never came back, I don't know why. And wouldn't it say that this is my it's yeah, so that's like £20. And then I think this session, this time is great. It's the same guy every. Yeah, like she probably finished at the time that they say. Different room speakers. I see what their sports centers like. Oh yeah, I think last year when we went to the gym. Yeah, I was going to go last year. Oh yeah, they were like you actually have to pay to go. Oh yeah, it was like £2. Oh. I don't know though. Don't quote me on that. But I think it was like. Yeah, I was going to say about it. Maybe if you showed them that Ken card, like Ken I knew. That's good. That's how I was here on like run on the. Oh no. It's nice, but I like at home. I live right next to like one of the biggest like preserved parks. Oh. So very yeah, they live in the I live 15 minutes from the centre. Oh, okay. And then university is the other side of the town. So it's like 30 minutes on the train. Oh, okay. Every day? Do you go in every day? Most days. I know some people are work from home, yeah. I can work from home 2 days a week. I usually work from home 4 days a week and then not work from home. Then I go to the office 4 days a week. And then work from home 1 day. Oh, okay. That's nice. But I have not. Do you have people there like you're right? No, yeah, because I'm the same. Like everyone in my team is like at least 30. Hiring. Oh, wow. But the university have other offices. Oh, okay. I'm off campus, so I can. So they were on campus, like yeah, but they work in HR. Are they degrees? So is there any other degree? Doing like the same, like science or because we have another. It's Broden and then Sheila, but she's not here this year. I think she's doing something this year. But they haven't hired any more because I know I was speaking to some senior sources. They have like 50 people. Like, there's so many people. But they are. We didn't hire another degree so she's in like finance or something else. So I never. I'll be stuff across, but I don't know. It's just like marketing. Yeah. I just social media. Oh wow. You see our dress and Darth Vader at the top of. Like, tower. So random. I think it's so funny like what people do to like catch attention and like brands like some like the huge brands or that you see like their TikTok pages it's like what actually is this? Yeah. Yeah. It's you know the ones that are friends with like everyone. Oh that's cool. It's kind of hard to take emotion out of it. It's so cool.
Okay, I think we've got everybody back. So let's crack on, okay? So I spoke to a few. In the break, and they said, yeah, we've done most of that stuff, A levels or GCSE or something like that. So it should not be too unfamiliar with you. But let's do a little bit something new stuff, right? So that it's not getting too boring. We've done the variance and the standard deviation, and they are great. I told you the problem with the variance is that it doesn't maintain the units, and therefore we take the square root, and that is called the standard deviation. But it has another, probably even bigger problem, the variance. Why it makes it a little bit sort of, sometimes might not work out the way we want. Could you think of a problem that the variance has in variability, another problem that the variance has based on its calculation. So here's again how we did the calculation.
It's influenced by outliers.
Bingo! Callum, you are absolutely right. The variance is incredibly sensitive to outliers. Why? Well, because we use the mean. And if the mean is sensitive to outliers, then of course any calculations that uses the mean is also sensitive to outliers. So the variance is sensitive to outliers. If the variance is sensitive to outliers, then of course the standard deviation is sensitive to outliers because we just simply take the square root. Yeah. So, god damn it, if we've got outliers, that's not good. Maybe we can come up with something that is not so sensitive, and that indicates the spread. So if you take notes, leave a little bit of space, because for the title of this, what we could do, for example, is, well, we calculated previously the distance of our numbers, the average distance of the numbers to the mean. What parameter is not sensitive to outliers? The median. Great. Why don't we just simply take the median? Because the median doesn't care about outliers. And instead of the squares, we could use the squares. But this time, we shake things a little bit up. What we do is we take the absolute value. So our data set, 1, 2, 3, 4, 5. We calculated the median. In this case, it's 3. And what we do is we just simply take the difference to the median of each data point. So we have 1 minus 3, but we are not squaring anything. We just simply take the absolute value, and the absolute value is indicated by 2 vertical lines. We take 2 minus 3 vertical line. 3 minus 3 vertical line. 4 minus 3 vertical lines. 5 minus 3 vertical lines. Right? So what do we get for the first one? First one, 1 minus 3 would give us minus 2, but we say screw the minus. This gives us 2. Yeah? What's the next one? 2 minus 3. What do I need to write? 1. 0.
1, 2.
1, 2. Fantastic. Now I've got, let's put them in order. 1, 1, 2, 2. Right? Now I have worked with the median. Can you give me the median of this data set now that I just written down? 1. You're absolutely right. So this is basically, how would you describe that? So 1, you're absolutely right. How would you describe this? What did we do? We took the median of the absolute difference between observation and the median. That's what we did, isn't it? And that is actually what this is called. It's a measure of dispersion. But if you write that 50 times in your report, you probably go mad, right? If you have to type that.
That's why it's called MAD.
And that is why it's called MAD. Exactly. It is the median of the absolute difference. So this number is called the MAD.
The absolute difference from the mean or from the median?
Of
the 1 to 5.
Median, there's 2 times medians in it.
Okay.
That is, actually, it's a very good question, Colin, because sometimes you also see the mean of the difference. And I absolutely hate that, because as a sort of Puritan, the MAD is defined as the median of the absolute difference to the median, 2 times median. Because we don't want any means in there, because the means are sensitive to outliers. Yeah? Happy with that? So we have range, we have variance, we have standard deviation, we have MAD as measures of dispersion, as measures of variability of our data. There are potentially more, but there are all sort of derivatives of these things. So let's not worry about that. So we can describe our data. Now, what we were dealing with so far, however, are data where we had only one data set, right? 1, 2, 3, 4, 5. So we only had one variable. That's why this is called a monovariate data set. Only one variable. 1, 2, 3, 4, 5. Height, for example, or the length of a cut or whatever. But sometimes life isn't that simple. Sometimes we have data that are connected with each other, that are linked to each other. So, for example, if I record two data that are closely linked to each other. For example, I record the height of somebody and the weight. So I take the first measurements, 175 centimeters, and the weight, I'll make this person a little bit obese, 78 kilograms. Now what we have all of a sudden is not just one data set, but we have two data sets where the data are linked to each other. So we would call that a bivariate data set. Of course, I could calculate for each column, I could calculate the mean, I could calculate the variance, I could calculate the standard deviation. Oh yes, we could do the median. I could do that for each one of them. But, and I can do that here for the weight as well. But I've got two data that are linked to each other. And I can now ask more questions. I can, for example, ask, is the height actually linked to the weight? I can build what is known as a correlation. And in this case, what would you say? Height, is it continuous data or discrete data? It's continuous. What would you say about weight? Absolutely right. So we've got two continuous data. And we say, for example, I measure the height, or I have the height. And that is sort of what I design in my experiment. That is what I've been given. And then I measure the variable weight, which is sort of directly linked to it. So in this case, we call this here, the height, the independent variable. And the weight is what follows from that, from this independent variable. Therefore, this is called the dependent variable. And of course, you have learned that we can use now sort of two dimensions to visualize that. We can, for example, say we plot on the x-axis. We always plot the independent variable. Always independent variable on the x-axis. So here it would be the height. And on the y-axis, we plot the dependent variable. And that would be the weight. Yeah? And if I, for example, took the data here from people, don't worry. I'm not putting you on the bathroom scales. It's not public humiliation here. What we would get is probably something like that, right? And this gives us a sort of an idea. The taller somebody is, the higher their height. So what we would see here is a positive correlation. positive correlation between weight and height. Height and weight. Okay. We could also see a negative correlation. Negative correlation would be independent, dependent, would be something like that. Yeah? The more I have of one, the less I have of the other. Could also be that I have no correlation. So that is negative. So for example, if I measure the height versus IQ, we would hope that there is no correlation with it. It's not that tall people are smarter or dumber than vertically challenged. Yeah, so that would be no correlation. And we can do these bivariate data predominantly with what we said, continuous and also continuous data. Yeah, great. Actually, I have drawn a sort of a straight line in there. And what we have here in this case is just simply one independent variable. This independent variable is usually, or always plotted on the x-axis, is also called the predictor variable, whereas the dependent variable, that would be y, that would be the outcome variable. And we could sort of describe that with basically a linear expression. So in this case, y equals mx plus c. M is the slope, and c would be the intercept between the line and the y-axis. So here, that would be the intercept, and the slope, that would be here the gradient, yeah, of this line. Actually, in statistics, people don't use m and c because they have other meanings. In statistics, it would be written as y equals beta 1x plus beta 0. It's exactly the same. It's just the statisticians love to use Greek symbols. Why? I have absolutely no idea why. It's exactly the same. Yeah. Oh, did I say mu? Sorry, no, that's not right. I wanted to write a y. Y equals beta 1x plus beta 0. But of course, there is no law in the entire universe that says we can have only one independent predictor. I can, for example, have in a trial, I can have, say, height. I can have income. I can have IQ. And I measure the weight. So these are all variables that I could measure in a trial. This would be independent. And this would be my dependent variable. That would be the outcome. Yeah. Could you envisage a scenario where, for example, height, income, and IQ could be an interesting thing to look at when I want to study, weight, for example? One can easily think of, I want to develop a weight loss drug, whatever they are called, Monjoy or something like that, yeah. And I want to see whether it works for rich people as well as for poor people. One could, for example, argue that maybe people who don't have a lot of disposable income can't buy that much food, so their weight will be reduced. So it could be a link between income and weight. Or dumb people only go to McDonald's and get really fat, or something like that. I don't want to put myself out here, but you can see that there are potentials. So we could call this one here x1. We could call that one here x2. We could call that x3. We can now write our outcome equals b1 x1 plus b2 x2 plus b3 x3 plus b0. So we have several predictors sitting there. Yeah. How do we draw that? Answer, we can't. We cannot draw that. I mean, with 3, you probably, now with 3 you can't, with 2 you can, if you do sort of, with X, Y, and Z axis. But with 3, like I've done here, it gets too abstract. But that is what's called a multivariate data set. Yeah? You don't have to have just one. You can have several predictors. Height, income, IQ, number of children, number of dogs, age. Hey, age would be a good one. Hey, let's put an age in. That would be x4. Yeah? And you will probably find that the weight is relatively not influenced by the income. It is probably not terribly correlated with the IQ. So please forget my previous comment about McDonald's and fat people. But it might be related to age. And that is something that we capture with multivariate data sets. We could also have another thing where we have height and the weight, so as we had before. But this time we are a little bit more brutal. We just say we don't care about the weight, really. All we are interested in is whether the person is obese or not. Yeah, so I measure the height. And now I say, don't care about the weight. I just look at you and say, "Bah, that's a fat cow," right? I say obese, or probably has to jump around in the shower to get wet. So slim, yeah, not obese. Things like that, yeah? You see the thing? Now, this here is still continuous. What is this variable here? Is it continuous?
Nominal.
It's not continuous. It is sort of, it's nominal, isn't it? Yeah, you're absolutely right. It's nominal. But what I can do is I can turn that into, I can code it sort of. I say, if the person is obese, I indicate it with number 1. If they are not obese, I indicate it with number 0. Yeah? What I do is I sort of converted the continuous data into a classification, if you like. Yeah? And what I do now is I actually do exactly the same that I've done before. I plot on the x-axis, I plot my independent variable, continuous variable. Independent, that's the height. On the y-axis, however, I don't plot the weight. I just simply plot the number of the classifier. Classification. And what numbers can this be on the y-axis? Sorry? 1 and 0. So 0 and 1. Yeah? So what I probably will find is that people who are if they are Diddy, might look a little bit like that. So I've got over the spread, I've got height, and they are not obese. But I also find people looks like that. Yeah, they're all on a straight line, basically. So you see here we've got some kind of classification. Can you see that? Yeah. I can actually also, I can't do a straight line like I've drawn before, what can I do is basically can do probably something like that. Yeah. So I can say, well, if you are very tall here, maybe we can say instead of the weight, let's do instead of height, let's do weight. It's more intuitive. If you have lots of poundage, you might be classified as obese, but you might not be classified obese if you are, for example, an endurance sports person. Yeah, muscle weighs more than fat, so you might weigh a lot, but you're not obese, and that is exactly sort of a classifier. This is called a logistic regression. Whereas what we did up here, this was called linear regression. That's where we have a straight line. Logistic regression is where we have these classifiers. Every day, you work with logistic regression. Believe it or not. You just don't know it. How come? When you look at your emails, do you get a lot of spam in your email?
Yeah.
Yeah? Mm-hmm. I don't, because I've got a spam filter. You probably have a spam filter as well, but it's not terribly sensitive. A spam filter makes a decision whether it's 0 or 1. Is it spam or not? You make a decision on the basis of what a person looks like. Is this person trustworthy or not? 0 or 1. Certain people, down here, not necessarily weight, but by the looks, they're down there. You say not trustworthy or trustworthy. We've got classifiers. And believe it or not, this is the basis of every sort of artificial intelligence or something like that. That is behind AI, that they do classifiers. Is this information important or not? Logistic regression, where you have these two categories, is absolutely essential for whatever data manipulation you do. You just don't know it, and you don't get taught.
Is logistic regression only with it's got two categories?
Excellent question. Logistic regression, the answer is yes. It can deal only with two categories. But what happens if we have more than two categories? If we've got, for example, pain level. What we would end up with is something like that. Yeah? And because it's statistics, we are dealing with what kind of data would that be? Yeah, what kind of data? So here we've got nominal data, two groups. This would be ordinal. What would you call this?
Ordinal regression?
You are absolutely right.
Yes.
Ordinal regression. Yeah. very, very common. If you have more than 2 categories. And that is where you start mixing, basically, continuous data with categorical data. Yeah? So, wrap up this session. What we have done is we discussed the different data types. We discussed how we can summarize the data in this exploratory data analysis. And we discussed that you can have some linear data, bi- or multivariate data. And you can also have different levels at the outcome of the data, either continuous or just 2 categories, then it's logistic, or several, then it's ordinal. And we've touched a little bit on what the data might look like already with these graphs. And after lunch, I suggest that we then look a little bit more into the graphical representation of the data. And because we have talked about it so much, we look at outliers. How do we find an outlier? What the hell is an outlier? And how do we deal with it? And then at the end, I show you also a little bit about R. Are you happy with that? I'll be back at 2 o'clock, is that right? No, 3 o'clock. I'll be back at 3. Ladies, gentlemen, thank you very much, and I shall see you later. Be good and enjoy your lunch. You are to
150.